Hey everybody, today we are talking about Unit 7.2, Instantaneous Rate of Change. So we left off our last lesson kind of looking at the difference between average rate of change, which happens over a course of 2 points, and instantaneous rate of change that happens at one specific point, because the distance between those original 2 points is so incredibly small, it's essentially approaching zero, making it 1 point. So we're going to do two types of problems today. The first, where we find the instantaneous rate of change from one specific x value. Okay, and then one where we find an expression that represents the slope for any point across the function. Okay, so we're going to be using that limit formula that we derived in 7.1. Okay, so remember, the instantaneous rate of change is the exact rate of change at a specific point, one specific point. Okay, and it's also known as the slope of the tangent line. So we want to just start to associate instantaneous rate of change and slope of the tangent line. You could be asked to do this problem using either of that wording, and you want to make sure you know that that means the same thing. They represent the same thing. Okay, and in order to solve that, we use the limit formula. Okay, remember that h is the distance between the 2 points that you would be finding the rate of change across. Okay, but here we evaluate h as 0 because we want to imagine that the space between those points is so incredibly small that there virtually is none, so that we're really just finding the slope at 1 point. Okay. This uses function notation. That's what f of x is, and f of x plus h. Okay, so we're plugging in our specific x value to the function. And then we're using the y values. We're using the output in the limit notation here to replace f of x plus h and f of x. Okay, which means that before we start the problem, we have to evaluate these two pieces of function notation. We did problems similar to this in 7.1, even though we were finding the average rate of change in most of those problems. We did set them up with f of x and f of x plus h to prepare us to do this limit formula. Okay, so our first example is at a given specific point. Okay, this is our given specific point at x equals 4. Okay, and our function is f of x equals x squared minus 9. And we're given the graph here. Okay, so essentially what we're trying to do is find the value for the slope of the tangent line, because remember, that's the same thing as the rate of change at one specific point, which means at that particular instant. Okay, so 1, 2, 3, 4. Here's x equals 4 on that function, okay? And if we had a line tangent to that 1 point, okay, it would look something like that. And we want to know, well, what is the slope of that line? That's what we're going to be solving here, the slope of that line. So the rise over run of that line. Okay, we can't just count the rise over run on the graph because it's only at one point, and you need another point to do rise over run, which is why we use the limit formula. Okay, so our limit formula, I'm just going to rewrite it over here. So m, the slope, because that's what it finds the slope. So the first thing that we need is f of x plus h and f of x, which means we need to take here this specific x value of 4, and we need to plug it into these two function notations. So f of 4, we're going to take 4 and plug it in to x squared minus 9. (16 minus 9), we get 7. This is the value we'll be using. Okay, now we'll do f of, well, not x, because we have a specific x value. It's 4. F of 4 plus h. That's for this component. So that means we're taking 4 plus h and we're plugging it into our function. So we're going to have to do 4 plus h squared minus 9. This component here, this needs to be FOILed. Do not just square each individual term. Okay, so we'll bring this expression back and just include the minus 9 on the end there to finish that out. You're going to have h's as part of your final expression, and that's fine. You need that. You want that. All right, so we have some like terms there to combine. Okay, so we have, and I'm just going to rearrange it into standard form. Okay. So this is my final answer for this component of f of 4 plus h. Okay, so all we've done is take our limit formula over here, and we've evaluated this using x equals 4, because that's what was given to us in the problem. Okay, so we set this up with x equals 4, and then we had to evaluate each of these two components in the function. Okay, so now we're going to replace those, because we have a value for f of 4 plus h, and we have a value for f of 4. We can actually do the computation here. Okay, so we have h squared plus 8h plus 7. That's our f of 4 plus h, minus our f of 4, which is 7. Okay, all over h. So we're just replacing these two function notations with their value. And then we're going to simplify the fraction, this rational expression, before we evaluate the limit. Okay, so plus 7 and minus 7, I'm just going to combine those like terms. I see that I can factor out an h from the numerator. Which will allow me to cancel with the h that's on the bottom. So I'm just left with h plus 8, the limit as h approaches 0 of h plus 8. It's been fully simplified, that expression. So now in order to evaluate this, remember when we algebraically did limits all the way back at the end of Unit 1, we can just take whatever limit we're trying to find and we can directly substitute that in. So that means we're just doing 0 plus 8. We're plugging in 0 anywhere that we see an h. Okay, but you want to make sure that your expression is fully simplified before you do that. Because if you tried to plug it in somewhere up here, you're going to get that it's undefined because you'll have 0 on the bottom. All right, but 0 plus 8 means that m, my slope, equals 8. So the slope of this line at this particular point, the 4, 7, has a slope of 8. Now, depending on the function and depending on the x value that you choose for your specific point of finding the value of the slope for that tangent line, the slopes could be very, very different from each other. Okay, so we're looking at this function here of x squared, and we're talking about these 3 different specific points of -2, 0, and +2. Okay, so it says put a line in there to represent each of those tangent lines for those 3 values. Okay, so here's x equals +2, here's x equals 0, and here's x equals -2. So if we had a tangent line to each of those 3 points, well, the slopes for each of those lines are all very different from each other, okay? This one is very clearly positive. This one's very clearly negative. This guy is going to be 0. Okay, so in order to evaluate the limit for each of those 3 points, that's a lot of work, right? This is all of the work that we just had to do to evaluate the limit at a specific x value. So essentially what this problem is asking me is to do that 3 separate times because it's giving me 3 different x values. Well, that's a lot of work to have to do that entire process separate times for every x value that you want to find the slope of that tangent line at. Okay, so instead, we can develop an expression that works for every x value on that function. So the way that we're going to do that is instead of using an actual specific x value, like plugging in 4 and 4 plus h, we're going to leave these in terms of a variable x so that we can do it for any x value in the future. So we're going to leave them as f of x, and we're going to leave it as f of x plus h. We're going to do the same process, though. We're going to plug each of these function notations into the equation we were given. We're just not going to do it for a specific x value. We're going to do it for a general. So this is the general equation. All right, so if I take f of x, so I take x and plug it into my function, well, that doesn't change my equation, right? That's x squared. So the f of x, when you're writing the expression, should always just be whatever function you were given. Now we're going to do f of x plus h. So that means take x plus h and substitute it into the function. So we would be doing x plus h squared. So we just did the same thing in the previous example, but instead of using a general x, we used a specific 4. All right, so again, this value has to be FOILed. Please make sure you actually multiply it out. Don't just square each term. Okay, and again, you're going to have h's and now x's as part of your final expression, and that's okay. So we're taking the value of what each of those function notations equals. Okay, and we're going to substitute those into the limit formula now. Just extend my paper here. Okay, so we're going to replace f of x plus h with x squared plus 2xh plus h squared, because that's what it equals. And we're going to subtract, we're going to replace f of x with x squared. You want to make sure you always use parentheses around this second expression, especially if it's more than one term, because you'll have to distribute the negative. Okay, so I see that these will cancel out. And I can, again, I could take out a GCF of h there. Or, I mean, you could just cancel it right here. If you wanted, those will cancel, and you'll be left with just one h on that. Okay, but what was really happening there? I took out the h. So it was 2x plus h over h, and that canceled. Okay, so I'm really looking at the limit as h approaches 0 of just what's left, which is 2x plus h. Okay, so once it's fully simplified, we can do our direct substitution, meaning take h equals 0 and plug it into your expression. So 2x plus 0 is just 2x. So that means that the slope for any tangent line on this graph, we can calculate by doing the expression 2x, meaning I give a specific x value, and now we plug it into that expression. Okay, so if I want to know what is the slope for the tangent line at x equals -2, well, I'll take -2 and I'll plug it into my expression. So the slope equals -4. Okay, what's the slope at x equals 0? The slope is 0. What's the slope at x equals +2? The slope is +4. So see how much quicker it was to then take multiple x values and calculate the slopes there once you have this general form of the slope of the tangent line. So you don't have to go through, you only do the limit process once rather than having to do it 3 times with a specific x value. You do it once with a general expression of x and x plus h. So we leave these as variables so that later on in the problem, we can plug in any specific x value that we want. Okay, let's do this process again. So instead of finding at each of these values individually, we're going to do it once for a general equation and then be able to use that for all x values. All right, so we start with f of x and f of x plus h. So we always start the same way, whether we're doing for a specific x value or we're writing the expression for all x values. Okay, so if we were doing a specific, we would actually have an x value here to plug into the problem, okay? So if we wanted to do just for -2 or just for +2, right? But since I have to find 3 of them, I want to do it in general so it doesn't take me 3 times as long. All right, so what is f of x? That should just be the function that you're given. So that's 4 over x. And what is f of x plus h? Well, that means take x plus h and plug it into the function. So that's 4 over x plus h. Okay, so this problem is going to be a little bit more challenging because our function is rational. It's a fraction. So we're going to be making some common denominators within the problem here. So we want to be prepared for that. Okay, so these are the two values we're going to use. That's what we're going to substitute into our limit formula. Okay, so we can set that up. So the slope equals the limit as h, so used to writing x, as h approaches 0. Okay, so f of x plus h is 4 over x plus h minus f of x, which is 4 over x. Okay, so you see in the numerator there, we're going to need a common denominator to put these two fractions together. Okay. So 4 over x plus h, I'm going to multiply top and bottom there by x, right, from over here to make a common denominator. And I'm going to multiply top and bottom of my second fraction by x plus h. So we actually have to give this the full x plus h and the x because this is one term. Okay, we can't split apart an x and a plus h. So you need both of those factors as your common denominator. Okay, so we'll simplify across the top here. We're going to make sure over here that we distribute that -4. Okay. So these problems, the hardest thing is the algebra. You have to be able to evaluate that function notation. And in something like this, we have to be ready to make a common denominator. Okay, so this is going to be 4x when I multiply here minus 4x minus 4h when I distribute to x plus h. Okay, and your common denominator is x times x plus h. I'm not going to distribute that on the bottom just yet because maybe something will cancel. All right, so in the numerator here, 4x minus 4x, that cancels out. So minus 4h is left over. X plus h, whole thing divided by h. So complex fractions still, okay, I'm going to multiply by the reciprocal. All right, so keep, change. So keep this. And we're going to multiply by the reciprocal of the denominator here, which is h. So we're going to multiply by 1 over h. Okay, you see we can cross cancel with the h in the top and this guy in the bottom. All right, so what are we left with? Just -4 over x times x plus h. Okay, so now we are ready and prepared. We can evaluate the limit here using direct substitution. So I'll just plug 0 into this fully simplified expression that I've gotten. So -4 over x times x plus 0. So x plus 0 is just x. Right? That basically cancels out. And x times x is x squared. So the expression for the slope of the tangent line for that function is -4 over x squared. So now I can take any x value that I want, plug it into this expression, and I can just do simple math to get the slope and very quickly find for multiple x values, rather than having to do this whole limit process for multiple specific points, right? Because the original question here asked me to think about -2, +2, and 4. So having to do the limit formula for each one of those separately, this problem would have taken 3 times as long. This way, I only had to do the limit once, and now I can plug in all of those x values pretty quickly. So the slope at -2 would be -4 over -2 squared, which is -1. At +2, -1. At 4, -4 over 16 is what? -1/4. Okay, so in a matter of seconds, I just found the slope for 3 different tangent lines because I had this general expression for the slope. Okay, so it is quite an involved process here, but we're going to spend a lot of time practicing. Okay, so make sure that you have all of these example problems down, and we're going to talk about this the next time that we are in class. All right, thanks so much for watching, guys. I will see you soon.